Hello, everyone, and welcome to the Mindscape podcast. I'm your host, Sean Carroll, and those of you who've been following my stuff over the years know that I'm very interested in quantum mechanics, the foundations of quantum mechanics, what it all means. And in particular, I'm a proponent and advocate for the many worlds interpretation of quantum mechanics. I think it's probably the right one, but there are smart people who disagree. So therefore, on today's episode, we're going to feature a smart person who disagrees. David Albert is a philosopher of physics at Columbia University who got his PhD in physics from Rockefeller, and he is one of the leading figures in the world on the foundations of quantum mechanics. He is not a fan of many worlds, of what we call Everettian quantum theory, and so we're going to dig into what makes him such a skeptic. Sadly, we didn't get quite enough time to talk about what approaches to quantum mechanics he is in favor of, but that's okay. Maybe we'll come back for a new podcast some other time. We're going to explain what quantum mechanics is, what the measurement problem is, what the many worlds theory says, and the particular puzzles he sees that he does not feel optimistic that many worlds is going to be able to answer. This is a very useful podcast to listen to if you're kind of interested in this area but aren't an expert, both because we sort of clear up what are the silly objections to many worlds and focus on what we agree are the important puzzles, the important challenges to many worlds. David knows perfectly well that many worlds is a plausible theory, but he just thinks that the obstacles to getting it right are not going to be solved, whereas I think that they are going to be. The other reason is because this is a masterclass in careful philosophical reasoning. David is extremely good about not using any jargon, either physics jargon or philosophy jargon, but also very good at very carefully, precisely, rigorously setting out what the issues are, looking at the different alternatives. So I personally do not reach the same conclusions from that analysis that David does, but I always have time to listen to him. In fact, I actually got a couple of new ideas just while we had this conversation. So I hope that you get some new ideas too. Let me just mention the occasional podcast notes. You are very welcome and encouraged to support Mindscape by donating on Patreon or PayPal. You can check out the website, preposterousuniverse.com/podcast to figure out how to do that. And of course, we'd love to get good reviews on iTunes or elsewhere. And with that, let's go. David Albert, welcome to the Mindscape podcast.
Glad to be here.
And we'll warn the listeners ahead of time that we're here in your apartment in Manhattan, and we have a guest speaker in the form of Leroy, the little dog. So if anyone hears barks, don't fear for our safety. That's all part of the experience. So I'll start with an amusing anecdote, which I read in Adam Becker's book about you. And by the way, I'm writing my own book on quantum mechanics, as my listeners know.
So you've told me.
And I'm going to rewrite that anecdote. It's going to be in there good. And it's about your experience as a graduate student at Rockefeller. Right. And you made the mistake of reading a book by David Hume, if I understand correctly. Right. And that got you interested in foundations. And what happened?
That's, well, there was that wasn't received warmly at Rockefeller.
This was in a physics department.
This was in the physics department at Rockefeller. There were, within fairly short order, proceedings instituted to expel me from the PhD program. This was back in the very late 1970s, early 1980s. So this was in dark old days. But worrying about issues like that was profoundly unpopular. I was, I got to stay in the program on the condition that I would I would work on a thesis topic assigned to me by the department instead of one that I chose. And the one that was assigned was clearly one that was thought to be good for my character.
Well, it turned out okay. Your character's in good shape now.
It was an extremely calculation-heavy. It was something about Borel resummation and phi to the fourth field theories, which people were playing around with in those days. It was extremely computation-heavy thesis topic. I had been in contact at that time already with Yakir Aharonov, who I had written to while I was a graduate student, telling him some questions that I was struggling with, didn't know what to do with, asked for his advice. He was wonderful. And I did go to him when I was given a pretty stark choice at a meeting in the dean's office, that either I was going to do a thesis topic assigned to me by the department, or I was going to leave the PhD program. And I said, okay, could I have a couple of days to think this over? And got in touch with Aharonov, who was very nice and had been very close at the time, for example, to Leonard Susskind, and said, I could talk to Lenny. Maybe we could transfer you to I guess he was at Stanford at that time. You could transfer to Stanford or something like that. But he said, you know what? It'll take you 2 years to complete this thesis. Maybe the best thing to do is put your head down, go through it. I can promise you that I'll offer you a postdoc with me in Tel Aviv when you get out. And you go to another place. There's a lot of respects in which you'll be starting all over. Don't do that. So I think that was good advice, and I did it. There's a nice little anecdote. I don't know if it's in the other book. I was, of course, the whole time fuming internally. And when I finally submitted the thesis, actually, there are two nice stories about this. If you don't have time for these,
go ahead. Yeah. We like stories. Those are good.
So one story is that as the epigram to the thesis, when I finally submitted it, there's a quotation, perhaps apocryphal, from Galileo to the effect that when he was finally released by the Vatican Inquisition, he stamped his foot on the ground after having recanted his doctrine that the earth moves. He walked out of the Vatican and stamped his foot on the ground and said, I think this is the correct Italian, said, eppur si muove. It moves. It doesn't matter what I said. It moves anyway. So I chose that quote in Italian as the epigram for my thesis. It took the department a couple of days to figure out what it meant, and there was widespread offense, and people were upset. The other nicer story is, so I submitted my thesis, and as you know, when you do a defense, people, just to sort of show that they've read the thesis, people never pass you completely outright. They say minor modifications, grammatical, this or that, given minor modifications, we pass, and you should submit the thesis to the dean's office within a week or so. So I walked out of that defense in a mood of the form, I'm not spending one more second of my life looking at this thesis or humoring these people. So I didn't. So I never handed in the final copy of my thesis to the dean's office. This was in 1981. And for years afterwards, there was a vague fear in the back of my mind that somehow, I hadn't fulfilled the full technical obligations for the PhD, and somehow, someday, God was going to use this to punish me, okay? So sure enough, 10 years later, in 1990, I get a call from the librarian at Rockefeller University who says, at the end of each decade, we compile all the theses completed over the course of that decade into a bound volume, and so on and so forth. And we find that we don't have a final copy of your thesis. And this was the call I had been having nightmares about for 10 years, and I froze in complete panic, collected myself a little bit, and did something uncharacteristically bold and sort of ballsy for me. So I collect myself and I say, "What? You lost my... I mean, what is your job anyway besides keeping track of things like, this is outrageous, this is unbelievable, I think this is appalling. No, I'm not going to give you my final copy of my thesis. You had better turn that library upside down and find that thesis, and I want to report within a week back from you about what your progress has been in finding the thesis. The woman says, I'm sorry, you're absolutely right, gets off the phone, calls me back a week later and tells me they found it. and needless to say, she was referring to an item which I happen to know did not exist.
And yet.
So that's a nice story about my getting my PhD.
And it's not as if, you were just rambling on at the time about what could quantum mechanics mean. Aharonov and you, wrote some very nice papers at that time.
Thank you.
That were useful for physicists as well.
Yeah,
right?
no, I thought it was I had a wonderful collaboration after that for several years in Israel with Aharonov, and just learned an enormous amount from him. I don't know that I've ever met anybody, and this is different from an intuition for how to solve foundational problems. I don't know that I've ever met anyone in my life who had as quick and as sure an intuitive grasp, which is almost a contradiction in terms, about how quantum mechanical systems are going to behave.
Right.
And it was just amazing. And, you'd be sitting in his office. He liked always to be talking to people. That's how he worked. So we were always, a couple of his graduate students and postdocs were just sitting around in his office in Tel Aviv all day and discussing. Once again, he wasn't so focused on what I would now call philosophical problems, but he just had this intuition about how you could make quantum mechanical systems do astonishing things. There were stories about him when he used to be at Yeshiva University in New York, where he would walk into people's offices in the philosophy department just in order to have something to do that evening and say, describe a physical effect which is obviously impossible, So people would say, I don't know, a man turns into an elephant,
right.
Or something. And Aharonov would go home and figure out a quantum mechanical way that this could happen. And this was the kind of exercise that lay behind many things that he discovered. And again, we would be talking about some concrete physical example, and he would say, it's going to do this.
Yeah.
And you would say, how do you know? Can you explain? He says, go home and do the calculation. It's obviously going to do this. I don't know how to explain it. And you would go home and do the calculation. He'd be right. It was astounding. It was one of these frustrating things also, because you figure if you're looking right at him while he's doing it, you're going to see how he does it. and
that never
this
work?
didn't turn out to be true.
Not really turning out to be true. I have Richard Feynman's old desk at Caltech, and I try to hide blank pieces of paper in the desk, hoping that they will appear the next day covered with equations. Hasn't worked either. So the problem that got you on this path then, presumably before this moment, you were a more or less conventional theoretical physics graduate student. I
think that's right. It's fair to say that my interests were always in a foundational direction. I think I remember. Maybe it's too long a story. To a first approximation, yes.
Yes, okay. Yeah. But then you discovered that you started thinking that the measurement problem of quantum mechanics really deserved more scrutiny.
I somehow, I'm sure many people went through this. This is nothing extraordinary about me. I hadn't heard of the measurement problem. And people often ask me to reconstruct, how exactly did you get from reading Hume to the measurement problem? And frankly, I'm not able to reconstruct that, and it probably involves an embarrassingly bad misreading of Hume.
But he certainly was not worried about the measurement problem in quantum mechanics.
But somehow, in the course of a long night of great intellectual excitement that began by reading Hume, by the time the sun was coming up, I had understood that there was a problem.
So how would, for our listeners who are not physicists or philosophers, how would you say briefly what the measurement problem is?
Something like this. if I ask how I know there's a glass on the table in front of us, people are going to give an account something like this. Well, there's light in the room, and some of the light reflects off the surface of the glass, and some of that reflected light enters my eye and impacts my retina and causes certain kinds of electrical excitations there, which in turn cause electrical excitations in my optic nerve and deeper into my brain, and yada, yada, yada. And after however many such steps, my brain has entered the state associated with the perception of a glass on the table. And I think it's fair to say that although we don't know yet, or might not have known at the time, what the detailed physical laws were governing all those steps, the story had better end up going something like that, because we can't imagine how else it might go. And it's important that at the end of the day, we can convince ourselves that each of those steps occurs in full accord with whatever the fundamental physical laws are. And it's pretty easy to show, once you start thinking about it from the right angle, that this couldn't be the correct account of how we know about the outcomes of certain experiments on quantum mechanical systems. If we were to play the game of imagining that the whole world is governed by quantum mechanical laws at a fundamental level, then it turns out to be pretty easy to show. And listeners might find it surprising that this is easy to show, because thoughts may occur like, my God, but a measuring device or a brain is something that's a collection of trillions of elementary particles. You can't possibly have solved the equations of motion of all those. No, it turns out that we don't need to. We're aware of a certain mathematical property of those equations called linearity, which makes it easy for us to say, given that I have a device here which would end up registering a blip over there if there was a blip over there, and which would end up registering a blip over there if there was a blip over there, then we have a way of calculating pretty straightforwardly what it would do in other circumstances. So very briefly, in quantum mechanics, or at least on the standard way of thinking about quantum mechanics, material particles like electrons, for example, can be in familiar situations, say, where they're located at point A, and other familiar situations where they're located at point B, but they can also be in other situations where in which there are all kinds of compelling experimental reasons to believe that that the appropriate way of describing them would be nothing like that you're in a situation in which in which asking about the spatial location of the electron would be analogous to asking about the marital status of the number 5, or about the length in meters of Catholicism, or something like that. Something that philosophers sometimes refer to as a category mistake. That the electron would be in a situation where it just didn't make sense even to raise questions about where it was located. Not that it's located in some position or other, but we don't know which one. But like I say, that's not what you would say about the marital status of the number 5, that I don't know what it is.
It's not our ignorance.
There is no fact about the marital status of the number 5. Good. And it turns out that you can show that what the quantum mechanical equations of motion entail, if they applied to everything, not merely the electron whose position you're measuring, but the measuring device and your brain when you look at the measuring device and so on, suggests that if you were to interact with this electron with a device designed to measure its position, the way things would end up would be in a situation where there fails to be a fact of the matter about the direction in which the pointer is pointing. There fails to be a fact of the matter about whether you're in a brain state that sees the pointer pointing this way or that sees the pointer pointing that way. And the idea is that these results, these implications of the equations of motion seem to be as directly at odds as anything could imaginably be with our empirical experience of the world.
And just to connect with, because I think some people probably have a little bit of exposure to these ideas, you're making the point that there's no such thing as the location of the electron in these states. What we often say is that the electron is in a superposition of different locations.
Exactly right.
So we can't help but, were we to naively follow the rules of quantum mechanics, end up in a superposition of brain states.
That's right. What I sometimes say to students is that what the linearity of the quantum mechanical equations of motion entail is that this condition of being superposed in this way turns out to be fantastically infectious.
Right.
You touch it and you've got it too.
Yeah.
Okay. Right.
And yet we never feel like we're in a superposition some sense. And so that's the measurement problem. So that's one way of saying the measurement problem, I guess.
Right. Or a stronger way of saying it, although, of course, I know you're anticipating things to come in putting it the way you did, but the initial reaction was more like, it's not just that we don't feel that. It's obvious that that's not the state we're in. Okay, it's obvious that it doesn't happen. We are as sure that that doesn't happen as we are of anything.
Right.
What happens in the laboratory is that we go and look at these pointers, and we end up with a perfectly determinate belief about where the pointer is pointing. In situations like that, which belief we end up with is usually a matter of chance. It's either here or there. The trouble is that what the quantum mechanical equations of motion predict is, first of all, that there's no chance at all, that the evolution of the world is completely deterministic. And second of all, that the state that you deterministically end up in is one in which there emphatically fails to be a fact of the matter about which way the pointer is pointing or about which way you think the pointer is pointing. And as I said, the usual reaction to this is not, oh, that's funny, that's not the way we usually feel. It was stronger than that. This is obviously false.
Yeah. But in fact, it was so obviously false that the idea of simply taking seriously the quantum mechanical equations, the Schrödinger equation, never occurred to the inventors of quantum mechanics, right? So the debates between Einstein and Bohr and others back in the 1920s and 30s and so on led to this additional set of rules, which we now call the Copenhagen Interpretation.
Right.
What are your thoughts on the Copenhagen Interpretation?
Well,
we should say what it is: wave functions collapse, etc. Right?
But the first thing to say about it, and the book by one of the many virtues of the book by Adam Becker that you mentioned earlier, is that he points out that as a historical matter, the words Copenhagen interpretation don't really refer to any single internally coherent set of claims. Different people claim to be enunciating the Copenhagen interpretation when they were actually saying quite different things. But, the thing you referred to, I think it's fair to say, is the thing that was standing there once all the dust settled after many years, and it's a claim like this, that, gee, if you really bite the bullet here, what you've got to say is that apparently there are two fundamental laws of the evolution of the physical state of the world, one of which, the one that sort of has sovereignty over the world in those situations when a measurement is not going on, are these linear equations of motion. And the other, which is in force when measurements are going on, is something called the collapse postulate, which selects out one or the other of these possibilities for you, makes it the case that when you measure the position of an electron, which is in a superposition of being at x and y, the measurement sort of has two steps. The idea of its being a passive thing vanishes forever from physics. Step one, although these aren't things that occur at two different times, but they're two conceptual steps. Step one is it changes the situation of the electron from one in which there is no fact about where it is to one in which there is a fact about where it is, and then reports to you what that fact is. The minute this was proposed, it was obviously wildly inadequate, or at least fell wildly short of our previous aspirations for physics. It involved, at the fundamental level, an English word, measurement, okay? Things behave differently when a measurement is going on and when a measurement is not going on. And it was clear that this English word, or the German word in von Neumann's book, where this was first clearly laid out, didn't have anything approaching the requisite precision to play that kind of a role in a fundamental physical account of the world. So the minute this was proposed, and I don't know what it was exactly in von Neumann's mind, but the minute it was proposed, it was obviously some kind of bad joke, okay? Or it was something that demanded, it was a provisional placeholder kind of thing that demanded much, much more elaboration. What's astonishing is that for, I think it's fair to say, so von Neumann's book was written, I think, at the very beginning of the 30s.
Yeah, 35. Came out.
For the next half century, the way that thought about this subject proceeded was by people going in what they should have realized from the beginning were ridiculous circles. So people would propose, a project grew up of locating exactly, being able to delineate exactly the location of the boundary between that set of circumstances where one of these laws applied and that set where other of the laws applied. So words like measurement were replaced by other words like macroscopic or thermodynamically irreversible or an indelible versus an unindelible recording or subject and object or something like that. And these were all, everybody should have realized, within 2 seconds that there was no improvement going on here at all, that all of these words were equally vague.
But even these words were invoked by, at best, a minority of working physicists. Mm-hmm. Most working physicists,
just didn't care
even
at all.
Today,
Right.
are very happy to just stick with that
But
thing.
it also, I think there may have been a symbiosis there. It gave the business of speculating about this a well-deserved bad reputation. I mean, perhaps the most famous of these speculations was one due to Wigner, who was, of course, very prominent and well-known physicist of the first half of the 20th century, person widely credited with introducing group theory into physics and thinking about symmetries in a certain way into physics and so on, Nobel Prize winner, so on and so forth, thought that the way to draw the line between these two domains of situations in the world was depended on whether or not they involved conscious systems. Indeed, there's an essay that listeners might be interested to look at, a famous essay of Wigner's called On the Mind-Body Problem, where he's thrilled about this idea for the following reason. It's been thought for a long time that the picture of the world we get from physics is hostile to certain ideas we have about ourselves as agents and as thinkers. There's no room in this picture for mind. There's no room in this picture for agency or freedom, so on and so forth. Wigner had this idea that it was precisely conscious agency that caused departures from the standard quantum mechanical equations of motion, that caused the collapse of the wave function. Indeed, he thought there was in this a new definition of the difference between animate and inanimate physical objects. What you mean by an inanimate physical object is precisely one that evolves according to the standard quantum mechanical equations of motion, and animate ones are ones that don't, that can give rise to collapses of the wave function. And Wigner thought this was great because physics had for so long seemed hostile to the idea of a non-physical mind somewhere in the world. It turns out, so he thought, not only is it not hostile, it requires such a thing in order to do its ordinary physical job. Good. Obviously, this distinction between animate and inanimate is just as vague as anything else. I remember, I swear on anything you want me to swear on, that as a graduate student, I witnessed Wigner at a conference in response to a question speculating to the effect that he thought dogs could likely collapse wave functions, but mice probably not. And you just say, you sit there and you say, this is not good, okay?
Right.
This is not the way to do physics. So it remained in that kind of terrible state for about 40 years. In the meantime...
Sorry, to be super duper fair, since in a few minutes I'm going to be advocating that every time you do a quantum measurement, the world splits into multiple copies, it's not the ridiculously of the claim that worries us so much as the vagueness of the
Absolutely claim. Right. Yes, I think that's a good point. But the business of having debates between, about dogs versus mice emphasizes just that problem, right? Yeah. Well, gee, who's going to? How are you going to win that argument, right? Right. I agree with you.
Okay, very good.
Basically, for about 50 years after von Neumann, that's where things stood. During that period, there were at least two what would later be recognized as very important developments, one due to Everett, which you were just referring to, and another due to David Bohm, which were serious attempts to make sense of this problem. But they were completely ignored at the time. Then finally, also in the early 80s, there was a third suggestion due to Ghirardi, Rimini, and Weber, which was along the lines of a collapse theory. And at that point, it's fair to say there began to be a critical mass of people talking about this and so on. Somebody else very much worth mentioning who belongs mostly to the earlier period is John Bell, who did take note of Bohm's work, who did take note of Everett's work, and I think who is widely thought of nowadays as the person who, in contrast to all the other people we were talking about before, Wigner and the macroscopic people and the thermodynamic irreversibility people, Bell is widely regarded as the person who showed how to think through these questions correctly, who established a sort of criterion as to what kind of thing could even be counted as a potential answer to this problem and what couldn't, and how you would begin to evaluate them relative to one another. He really set the field in a kind of order that I think the useful and productive parts of it have been following ever since.
Right. So we have the measurement problem. There's this weird thing that if you take the quantum mechanical equations, by which, Schrodinger's equation is the most obvious version, but there's sort of different ways of writing it. If you take those seriously, we seem to run into a conflict with experience, with what we see about the world. Right. That it says that we should ourselves evolve into superpositions. Right. So you've mentioned these three different ways of tackling that problem. We don't have to be historical. We can be logical. Do you have a favorite way of introducing the platter of options?
Of introducing the platter? Yeah. Bell nicely said in a paper that what the measurement problem shows is that either the Schrodinger equation isn't everything or it isn't right. Right. Okay. Now, your favorite interpretation is going to deny both of those, but this is a good way to begin to understand what's going on. The thought was either we need to... So there was this this standard way of representing states of quantum mechanical systems that came along with quantum mechanics, quantum mechanical wave function or the quantum mechanical state vector. That vector, unambiguously ends up a certain way at the end of a measurement process, and it ends up in a way that doesn't contain information about what the result of the measurement was, and indeed, on the standard way of interpreting it, denied that there was a fact about what the outcome of the measurement was. Bell said, look, there are two ways I can imagine dealing with this. One change the equations, okay? Change the equations such that they do evolve this wave function or state vector in such a way that it ends up associated with one or another particular outcome of this experiment. Indeed, among the things you would have to change about the laws of evolution is that they'd presumably no longer be deterministic. They're now going to be stochastic, because our experience is that sometimes you get this result and sometimes you get that. That's one strategy. That's referred to as writing down a theory of the collapse of the wave function. This is the strategy that's most continuous with the kind of thing that von Neumann was originally imagining. There's another...
And just parenthetically, even though it doesn't get that much attention among philosophers of foundations, Roger Penrose's efforts are in this direction.
That's correct.
An explicit theory of the collapse of the wave function.
That's correct. We might talk later. I think there are reasons why GRW's strategy is probably better than Penrose's strategy.
So GRW being three guys who have a different theory of the collapse of the wave function.
Correct. But that's right. Penrose's is another theory in this family, or within this tradition. So that's tradition number one. Tradition number two is to take the other horn of the dilemma that Bell spells out. It might be that the standard laws of the evolution of this quantum mechanical wave function that we have are perfectly true, but the wave function itself might not amount to a complete description of the physical situation. You have to add other variables. These variables, for unfortunate historical reasons, were called hidden variables. But if you study something like Bohm's theory, they're the opposite of hidden. They're the thing you see.
Yes,
right.
And Einstein had sympathies along this direction.
Yes, he did. That's right. That's what he seemed to want. And that's what the EPR paradox appears to be an argument for. And most people would say that the best example we currently have of a theory along those lines, although also there are several, is one due to David Bohm in the 1950s. There's a, sad. I mean, the story, as you hinted at, and I don't want to get too sidetracked here, of the way this work was ignored and the mechanisms that allowed the theoretical physics community to ignore them are sad and in many ways appalling. In the case of Bohm in particular, one of the things that allowed people to ignore his work was the work of the McCarthy Committee in the 50s. He was harassed out of the country soon after publishing his theory. That was something that made it much easier to ignore his work. I've often thought, somebody like Becker begins to make a stab at this. I've often thought that if you were to trace the sort of the history of people's reactions to foundational problems of quantum mechanics, you'd get a whole underground history of the 20th century, and all kinds of forces come into it. McCarthyism comes into it. In Russia, dialectical materialism comes into it. The rise of modernism in the beginning of the 20th century comes into it. It would be a very interesting story to trace out in detail. But anyway, that's a side issue. Then there is this other more radical, more heroic, more exciting tradition of Everett, which wants to...
the third horn of the dilemma?
The third horn of the dilemma, which Bell doesn't anticipate in this, in the description I just referred to, where you're going to insist, no, the quantum mechanical wave function is a complete description of nature, and moreover, the standard linear quantum mechanical equations of motion without the collapse are always obeyed. How do I want to put this? Everett suggested in his paper, and the paper is at a couple of points crucially unclear. This was apparently not Everett's fault, but the fault of his very unresponsible, in this case, thesis advisor, John Wheeler, who muddied and dulled Everett's point all over the place because he was afraid of Bohr's reaction. Indeed, there are, I just recently read Becker's book, so I'm referring to it a lot. There are astonishing letters in Becker's book that I'd never seen before of Bohr, of Wheeler trying to sort of, assure Bohr that Everett wasn't really criticizing him, that, could have been lifted out of a Soviet show trial. It's just mind-boggling.
Yeah, there are two things that struck me, because I read Adam's book and many other things for writing my own book. And so Everett was a graduate student of John Wheeler, and Wheeler himself had worked with, wasn't the student of, but had been advised and mentored by Niels Bohr, who was the granddaddy of the Copenhagen Interpretation.
Right.
And one, like you say, is that the reaction was both from Wheeler, who was afraid, I don't know if afraid is the right word, but certainly reluctant in a very explicit way of crossing Bohr and everyone else in the Copenhagen. But also the many letters that came back and forth from Bohr's acolytes in Copenhagen, some of them directly to Everett, and just being so dismissive and so misunderstanding in it, and you feel bad for Everett. But the other one is that, Everett, as someone who made this contribution as a graduate student and then left the field and did other things, there's his times in physics when someone does something great because they were in the right place at the right time, not necessarily because they were the smartest person around.
Right.
But you read, what Everett's writing, and he was the smartest person around.
That's true.
He understood all of the implications of what he was saying.
I think that's right.
And, he left academia because he wanted to leave academia, as far as I can tell.
I think that's right. And the flip side of this, there is this horror of the way Bohr ruled things. The flip side, I must say, he's one of the people, if I could pick to meet a historical figure, because he must have been somehow the most charismatic human being in the history of the world. And there was just this long string of brilliant people who would spend an hour with Bohr. Their entire lives would be changed. And one of the ways in which their lives were changed is that they were spouting gibberish, that was completely beneath them about the foundations of quantum mechanics for the rest of their lives. And you want to know, how did this guy do this?
And they revered him. There's a quote from Wheeler saying, the thing that made me convinced that there were people like Jesus and Moses and Buddha was meeting Niels Bohr.
It just, boy, do I want to meet this guy.
Because it doesn't come across in his writing.
It doesn't come across in his writing at all. At all. There is what's usually advertised as the most detailed and elaborate and sustained statement of Bohr's view is his response to the EPR paper. And anybody who's tried to read this, it's just really hard to see what's going on. And I don't know if you've heard this story, but a couple of years ago, Shelley Goldstein happened to discover, I can see by your face that you don't know this story. This is an amazing story. That the standard version of Bohr's response to the EPR, the one that was almost exclusively the template for every reprinting of it over a period of about 50 years, had 2 of the pages reversed.
I did not know
and
that.
Nobody ever noticed this, okay? So you have, anybody my age, your age probably a little less, has had a long history of the minute you bring up a worry about the foundations of quantum mechanics, people say, why do I have to waste my time on this? Bohr settled all this
Bohr figured it out
a long time ago. And you say to them, great, could you tell me what he says? And they say, no, go read the paper, okay? And it's obvious that none of the people who were saying this ever read the paper,
Right.
okay?
Yeah.
It's just mind-boggling.
Okay. And there's a whole bunch of other anecdotes. We encourage people to read Adam Becker's book. We'll have Adam on the podcast
Right.
at some point. It's a fascinating history of the foundations of quantum mechanics, which is an understudied field. So let's do Everett first, because it's my favorite. So what was Everett's solution to the measurement problem?
The way that quantum mechanics mathematically depicts these states of an electron, for example, in which there fails to be any fact of the matter about whether it's located at A or located at B, is by means of an addition of two vectors. The superposition of being at A and B is represented by the state vector associated with being at point A plus the state vector associated with being at point B. And the kind of state that the equations of motion predict that you're going to be in at the end of one of these measurement processes looks like a state in which the electron is A and the measuring device registers it to be A and the sentient observer sees it to be A, plus the state where it's at B and the measuring device registers it to be at B and the observer sees it at B.
And this is a nice way to put it because it really drives home the difference with classical mechanics, right? In classical mechanics, an electron can be at A or
Right.
be at B. There's no such thing
Correct.
as being at A plus B.
Correct.
That's just not a thing.
That's
But in
just not a
quantum
thing.
mechanics, you can take any two states and add them.
Absolutely right.
And
Right.
be in the superposition of both.
And be in some distinct physical state
Right.
that has its own distinctive physical properties. So Everett's idea was to interpret the kind of state that I was just describing, speaking crudely here, and he was more careful than this, but we want to be a little fast here, as one in which there were two observers or two experiences of the world being depicted, okay? In one of which there is a particle at A, and there is a measuring device that registers it to be at A, and there's an observer who sees it at A, and in the other of which there is a particle at B and a measuring device that registers it to be at B, and an observer who sees it to be at B or who knows it to be at B. And that in some sense there are really two things there. There are, as it were, two internally coherent stories or worlds going on there. It follows immediately that, of course, we wouldn't be aware of this kind of splitting because our mental state is either seeing it at A and not at B, or seeing it at B and not at A. So Everett's idea was maybe there is a way to take exactly what the standard quantum mechanical formalism had always said literally. Maybe the arguments that we were referring to before, to the effect that we know this not to be what happens at the conclusion of a measurement process, is wrong. Everett often compared it in what I always thought was a very nice metaphor with consequences of Newtonian mechanics, okay? And Newtonian mechanics has what seems at first like the very counterintuitive prediction that the Earth is in motion, that it's moving very quickly. And, you know, one would tend to object at first, that's impossible, we would fall off, so on and so forth.
We would feel it.
Right. And Newton, or I don't know what the history is, but Newtonian mechanics has the resources to respond to that by saying, no, you haven't worked out the problem to the end. It turns out that the very same laws that predict that the Earth is in motion predict also that if that were true, you would think it wasn't, okay? Right. If that were true, you wouldn't feel it. And something very much like that is being done with the linearity of the quantum mechanical equations of motion in the case of Everett. This same linearity that leads to this very puzzling and apparently false prediction of superposition, okay, also predicts that if that were what was going on, you wouldn't know it.
Right.
You would think otherwise. You would, as a matter of physics, as a matter of your physical behavior, you would testify to the contrary if you were interviewed about it. So there is a sort of very exciting, very pure, very radical, an early fan of Everett was Sidney Coleman at Harvard, who used to go around giving a lecture that I thought was very aptly named about Everett. It was called Quantum Mechanics in Your Face. And the idea was, no. It doesn't need to be prettied up or uglied up or something like that. It doesn't need to be dressed up or modified. Take the thing completely at face value, but calm down and interpret it carefully and precisely, and you'll see that what it's depicting, you'll see a way of locating in it exactly your empirical experience of the world.
Okay, let's put aside, one can talk about the many worlds interpretation for hours, but I want to skip over the boring parts. There are what I consider to be hilariously unconvincing objections to the Everett interpretation, like I just don't like all those worlds kinds of things.
Right.
And there's also what
if you have objections like that, physics isn't the field for you.
There's a lot of things that are going to be flying in your face of your intuition.
Right.
There are also what I take to be convincing arguments for Everett. There's a sales pitch that I like to give. Let's take both of those, into as if they were on the table and move on, because I think that your attitude is you wouldn't object to Everett in the same way you object to Copenhagen just because it's vague and ill-defined.
Right.
You just don't think it quite works.
Yeah, that's right. I mean, basically, look, and preparatory to this, I don't want to, even though it might enhance the excitement of the podcast, I don't want to be more dogmatic here than I actually feel.
No, that's right. You're not playing a role. Let's tell the truth.
Right. So that having been said, let me say what I take the situation to be. There's a very obvious puzzle about Everett, which can be brought up very easily, although when you try to precify it, it gets complicated in all kinds of interesting ways. But crudely speaking, you say, look, quantum mechanics, as it's usually formulated, is a chancy theory. It's a probabilistic theory. Moreover, that's not merely a sort of curious feature of it, a peripheral feature or an unimportant feature. It's absolutely at its core. The reasons we think we have, the empirical reasons we think we have for believing that quantum mechanics is true have to do with experiments that we repeat many times and obtain results in terms of large frequencies that we think bear out those probabilistic predictions. Those probabilistic predictions, that chanciness, is absolutely at the heart of what we take to be our compelling reasons for believing that the theory is true in the first place. And the obvious question that comes up right away is that, look, if Everett is telling us he's got a way of understanding the deterministic equations of motion to be true under all circumstances, there's just a very prima facie tension between the claim that the laws of the evolution of the world are completely deterministic and the appearance of these pervasive chancinesses or probabilities in our experience. That, on the most primitive level, as a sort of, first pass, is what's puzzling, is one of the things that's puzzling, not in terms, like you say, of being unexpected or surprising or counterintuitive, but on the level of coherence.
Yeah.
Okay? If this theory is supposed to explain our experience, how does it explain our experience of these chances?
I mean, at the very least, both people pro and anti-Everett agree that the usual way of talking in quantum mechanics, that there is a probability of 30% I will see the spin up,
Right.
can't be exactly right. I
Right.
mean, it might be, maybe you talk as if that's true,
Right.
maybe it gets you through the day, but
Good.
what actually happens is that with 100% probability, you evolve into multiple people.
Correct. So there's a long history of trying various, I think, very imaginative ways, and ways from which we've learned a lot about the question of what probability talk means more generally, of trying to come to terms with this. There was an attitude which is now more or less forgotten, but I think was very clever. This was certainly, for example, Sidney Coleman's attitude and other people's attitude, that they pointed out that something that was a feature of these deterministic equations of motion is that if you did an experiment, say, measuring the z-spin of an electron that started out with a definite spin in the x direction, and our experience of those measurements is that half the time they come out z-spin up, half the time they come out z-spin down. You just look at the equations of motion, how they describe a situation in which you repeated an experiment like that many, many times. And it turns out you can prove a theorem very easily that as the number of times, call it n, that you've repeated that experiment goes to infinity, the world approaches a funny state in which, even though there is no fact of the matter about how any individual one of those experiments came out, there is a fact of the matter, and this seems like almost like a contradiction, there is a perfectly definite fact of the matter about the proportion of them that came out up and the proportion of them that came out down. And in the limit as n goes to infinity, that proportion approaches exactly 1/2. And lots of people were seduced and excited by this result.
Did Everett himself have an argument along those lines?
I think he did. I think he, it's a little, like I say,
it wasn't included in the.
That's right. I haven't. Something I need to do and have never done is read all the original Everett stuff, which is now available, although only pretty recently. In the published part of his work, that argument isn't really clear. But I agree with you in your assessment of Everett's brilliance, and I would suspect he was aware of that argument, and he was just obliged to hide it from Bohr because it was too good,
But we have other arguments now. People are still trying.
Right. So anyway, that for various reasons didn't work out. I mean, I guess one of the things to say about it is that before you actually do get to the limit, the theory is adamant that there are no facts about anything, okay? And we don't, in fact, do infinite numbers of experiments and so on. So there were those things. Since then, I think it's probably fair to say that in, like, the late 70s through the early 90s, there was less excitement than there is now about this interpretation. And I think a lot of it was due to this difficulty of seeing how you could make sense of probability talk. Since then, there's been a very interesting and very lively revival of attempts to make sense out of that probability talk. And there are two big traditions that have come up. One tradition, which is associated with names like David Deutsch and David Wallace and lots of people around Oxford, something that's funny and noticeable about foundations of quantum mechanics is that even though all of us grew up with telephones and so on and so forth, attitudes about the foundations are incredibly geographically well-defined.
Right.
And Oxford was for many years the sort of isolated epicenter of sympathy to the Everettian view. Anyway, there is a view that goes like this. You start out by saying, okay, you're right. That is, you say to the critics, you're right. There are no probabilities here. I take it back. You won't hear me use the word probability anymore, okay? They say, take it seriously. that the only correct thing to say about what's going to happen to you when you make this measurement is that you're going to split, okay? You're going to split in this particular way. Pose the following question. Suppose that you knew that that's what was going to happen to you. How would it be rational for you to behave, okay? What kinds of bets would be rational for you to accept or decline, so on and so forth? And these guys claim to have an argument, and I think it's an argument that doesn't work, and maybe we'll get a chance to talk about it a little bit. But they claim to have an argument that it just so happens that in a world like that, the kinds of bets that a rational agent would accept or decline would just happen to be exactly the same ones that she would accept or decline in a completely different universe, which was chancy, okay, which had something like the von Neumann picture. And so the idea was, you're right, there are no chances, but the roles that chances actually play in our lives, both in our practical lives and in our cognitive lives, are more or less exhausted by these claims about which bets we would make. And what we've got here is a different universe than the one we thought we were in, a fully deterministic universe where we know what's going to happen, but where it just so happens we can show that if you took yourself to be in a universe like this, the kinds of bets you would make, the kinds of decisions you would make about how to behave would be exactly as if you were in a different chancy universe. And it's that match that's all that we mean when we say the universe is chancy in a way that it appears to us to be.
I mean, if it's possible, I would love to hear the germ of your objection to this.
So here's the germ of my objection. I'll try to say it. We'll achieve some compromise between saying it clearly and saying it concisely. And maybe I'll try to say it concisely first, and you can make me say it more clearly. Concisely, it's this. These strategies all depend, these arguments depend on, so the kinds of things these arguments purport to show is that, if you have, if you want to do any kind of decision series, so there's a whole branch of logic and mathematics and philosophy called decision theory, where people try to sort of axiomatize and lay down clearly what it means to make a rational decision. And in order to know what decision you need to make, you need to decide in advance something you wish to maximize. You may wish to maximize longevity or happiness or profit or something like that. But given a decision about what you wish to maximize, and given some picture you have about how the world works, what kinds of what kinds of actions have what kinds of probabilities of leading to what kinds of results, there's an algorithm that people try to develop in decision theory that you can feed all this into and decide what you want to do.
And the axioms seem fairly unobjectionable. Like if you prefer A to B and B to C, you prefer A to C, right?
So on and so forth.
Yeah.
There's a nice old joke, which it's worth bringing up, of Sidney Morgenbesser's, who used to be in the philosophy department at Columbia. Sidney said, "What is it that you maximize in Jewish decision theory?" Answer: regret.
Still, though, fits the axiom.
Good. Anyway. The thought of these decision theoretic arguments for Everett is as follows. We take your preferences for cases where the world is not going to branch. You prefer the outcome to be more money rather than less money for you, or something like that. And the structure of all the arguments is, given your preferences for non-branching futures, given your preferences among non-branching futures, we can derive, on pain of irrationality, what preferences you must have among branching futures, okay? So given the amount of money that you're willing to pay to make some non-branching future come true, we're going to be able to deduce, on pain of irrationality, how much money you'd be willing to pay in order to have a certain branching future come true. And what they claim to be able to show is that the amount of money you would pay to have this branching future come true is exactly the amount you would pay to have one branch come true with a certain probability and have the other branch come true with a certain probability. Good. In a very concise statement of the objection. And this sounds very simple, and it's amazing how long it took for people to see it because the arguments were couched in a way that made it hard to see. Look, it's just nuts to think that your preferences among non-branching futures could in any way constrain, on pain of straightforward irrationality, your preferences among branching futures. The branching futures are a whole new set of flavors available to you that become available only once you start considering. So, for example, you may be somebody who, under normal circumstances, I don't know what, prefers chocolate ice cream to vanilla ice cream. But if you're suddenly offered a new option, there can be two of you. One of them has chocolate ice cream. One of them has vanilla ice cream. You might have a taste for variety or something like that, which is simply not going to show up in any of your non-branching preferences. Okay, so there is, and I think when you put it this way, the whole strategy becomes obviously nuts, okay? You're not going to have, on pain of irrationality, you may think these tastes are weird and so on. That's not what decision theory is about. Like we were saying, you can choose to maximize anything you want. Profit, longevity, regret, whatever you like, okay? The decision theory is just supposed to tell you what you're supposed to do. These guys are arguing that once we know your non-branching preferences, unless you're completely irrational, we also know your branching preferences.
Linearity
that just couldn't be right, okay? That couldn't possibly be right, because once the branching preferences are put on the table, you can choose among these two. You got a whole bunch of different stuff to choose between. The thought was that your preferences among branching cases must somehow leave a trace or show up among your non-branching preferences in a way that's sufficiently strong to fully constrain your preferences among the branching cases. I think this is just wrong, okay? Let me see if I can give a more concrete example. So here's a standard example which people in the decision theoretic tradition use. Imagine the following kind of superposition. You have $100 and the rest of the world is in state A, okay? And you have $1 and the rest of the world is in state B, okay? Imagine a superposition of those two. You have $100 and the rest of the world is in state A, plus you have $1 and the rest of the world is in state B. Good. Moreover, let it be stipulated that among the non-branching options, that is, you have $100 or you have $1, you don't care about the rest of the world. You only care about how much money you have. So you have no preferences among, you have $100 and the world is in state A, and you have $100 and the world is in state B, and you have no preferences among, you have $1 and the world is in state A, and $1 and the world is in state B, but you prefer $100 with A or B, any state with $100, whether the rest of the world is in state A or state B, to any state with $1 and the rest of the world is in state A or state B. Good. Then they say, suppose that's true. Now consider the following two superpositions. $100 in state A plus $1 in state B, and $100 in state B plus $1 in state A. They say you couldn't have a preference for one of those over the other because you've already made it clear that you don't care about the difference between A and B. That's what shows up in your non-branching preferences.
Yeah.
Okay?
It kind of makes sense to me, I got to admit.
Good. So let's go. Let me actually, to make this even more clear, let me back up a tiny bit. I'll go through it here, and then maybe we'll back up when we need to. Right. Okay. Yeah. Okay. Suppose I say, part of the state of the rest of the world is in state A, I'm fat, and in state B, I'm thin. Okay? I don't care about how fat I am. That is, what I mean by I don't care how fat I am is I have no preferences between $100 in fat and $100 in thin, and I prefer $100 fat or thin to $1 fat or thin. So I have no preferences about my weight. But I say, now I'm confronted with the branching preferences. And I say, I think I'd kind of like to be rich in the branch where I'm fat, because I think more of me is going to be there. Okay? Or something. Now, we don't have to have a discussion about how reasonable this is.
No, you're just saying it's a logical possibility.
It's a logical
I don't care whether I'm fat or thin, but
that's right.
if
that's right.
Conditionalized on being fat, I want more money.
Exactly. Yeah. Okay?
Or vice versa, I guess.
It was always, and you're familiar with this example. You use this example in some papers of yours for slightly different reasons. But everybody thought, and it seemed very innocent to say, of course it's not going to matter if you permute the fat and thin. You've already told us you don't care about that. They weren't careful to attend to the fact that what they meant by saying, you've already told us you don't care about that, is that it doesn't show up in your non-branching preferences. Nothing about, you're having those non-branching preferences is completely consistent with your having all kinds of different preferences among different kinds of branching that might occur. Okay? So I just think, and the minute you start to think about it that way, it seems to me you immediately say to yourself, my God, what could we have been thinking? Of course, the branching preferences are just a whole new set of options that you have. Once those are put on the table, what makes you imagine that you could have deduced as a matter, on pain of pure inconsistency, your preferences among the branching options, just from your much more limited set of preferences among the highly special non-branching options. So that's in a nutshell why I think those arguments don't work.
Do they have an obvious response to this yet, or is this the ongoing dialogue?
There is, I think it's fair to say there's an ongoing dialogue, and I don't want to put words in people's mouths. There are various other principles that are sometimes cited in decision theories, things that go under names like dichronic coherence and so on and so forth, which are sometimes people try to bring to bear in these situations. I think they're beside the point. I wouldn't say that anybody's given up and rolled over, although I do think, for example, David Wallace's claims about what this kind of argument establishes are now a little bit more modest than they used to be, that they're clearly showing the consistency of such a thing,
right,
but not necessarily the rational necessity of such a thing. But I don't want to put words in David's mouth. That's my impression. It has gone back and forth. There are attempts to justify some of these principles. For myself, and it took me a while, in the evolution of my own thinking about this, I had thought of this so-called fatness example early on. It took me a while to see the general point. Okay, right. The general point I now see is these branching options, these non-branching options, are just a tiny fraction of the actual options you have once branching is put on the table. where did you get the idea that you could infer everything about your preferences among the branching cases from your preferences among the non-branching
Yeah,
cases?
because I think I read stuff by you about the fatness example,
Right.
but I found it wholly unconvincing. But
Right.
this point makes perfect sense to me.
Good.
That there can just be correlations between preferences
Right.
that couldn't have existed
That's
in the
right.
non-branching
That's
universe.
right.
Yeah.
That's right.
Okay.
So I think that's a much cleaner way to make the point. And as you just said, this wasn't the way I presented it in earlier writings. I had very specific examples. Now, it took a while to understand that these are examples of a very general, very simple point. And I don't know if that point has been made in writing in such a way that it's really gotten the attention of advocates of this point of view. And maybe we'll just have to wait a little to see how it strikes them.
Speaking of waiting a little, we're clearly not going to do justice to GRW and Bohm. That's
Sure.
okay.
Right.
Some other day we will. We might as well do justice to Everett. So
Sure.
you said there's another way to get the probabilities that
Sure.
you also don't agree with.
Sure. That there's a way. So, and here's where I want to be a little less dogmatic. I think there's a pretty cut and dried argument, as I've just been describing, against the decision theoretic point of view. There is a point of view that's associated with, among other people, you about this, that I've been thinking about for much less long because it's been proposed more recently, and I'm at least at this stage more puzzled about. But it's fair to say that I have worries about it that look to me to be serious. So if you want me to describe the view. So
I will chime in.
So it's something like this. One of the original ways we had of putting the worry was, look, where does, or maybe I didn't put it this way, but here's a way of putting it at this stage of the discussion that'll be useful. We're about to do a measurement of the z-spin of an electron whose x-spin is definite, or we're about to do a measurement of the position, maybe that's easier to understand, of a particle which is in at the moment the superposition of being located at x and located at y. And we say, look, if Everett is true, I know exactly what's going to happen. There are going to be two of me. One of them is going to see the particle at x. One of them is going to see the particle at y. End of story. Everything is deterministic. And what's puzzling about this is as follows. If you consider any other circumstances in which we've found it sensible to say things like the probability that x is going to occur or the probability that I'm going to see x is 50%, say. Now, we don't have a fully satisfactory consensus on a correct philosophical analysis of chance, but sure as hell, whatever it means, one of the things it implies is that there's something about the future of which I'm not currently certain. Okay? There may be any number of reasons for my not being certain about this aspect of the future. It may be that the fundamental laws of motion are inherently chancy, and for that reason I can't be certain about the future, no matter how much information I may have about the present. Or it may be that the laws are perfectly deterministic, but there's some information about the present that I'm missing because it's very difficult to obtain, because it's very microscopically detailed or something like that. And it may be some combination of those two factors. The worry in the Everett case is there seems to be nothing relevant to what I'm interested in here about the future when I'm preparing to do this measurement of the position of the particle. There seems to be nothing relevant about the future of which I'm currently ignorant. I know exactly what's going to happen. There are going to be these two guys. One will see the particle at x, one will see the particle at y. End of story. So you say, where does anything like chance have an opportunity to get a foothold? Chance requires uncertainty, okay? Remember, and it's helpful here to contrast this with the decision theoretic strategy. The decision theoretic strategy took the following route. We agree. There's no room for chance here. There's no chance here. All that's going on is that the decisions that a rational person is going to make would be the same ones they would make under these other circumstances where there is chance. So call it pseudo-chance or something like that. Good. Here's another approach. Somebody says, let's look at this process in a little more detail. Imagine that there's an interval between the measurement actually being carried out and my looking at the measuring device. But I know that the measurement has already been carried out before I look at the measuring device. At that point, it seems fair to say, I know that I'm now already either in the electron was at point A world or I'm in the electron that was in point B world, but I don't know which. So here it seems as if we have the sort of thing we wanted. We have some genuine uncertainty. Once we've got uncertainty about the future, that is, I don't know which one I'm going to see when I look, it feels like chance has a chance to get a foothold in a not incoherent way. There are all kinds of questions which we could discuss in more detail. Okay, but who says we always have this interval? And in some sense, isn't this interval coming too late and too late in the game? Put those all aside, because I think you guys have interesting things to say about all of those.
Us guys being in the paper I wrote was with Chip Siebens, who's
right.
Now my collaborator, my colleague at Caltech,
right,
in the philosophy department,
that sounds more promising. This is going to be a way to get real old-fashioned chance back in the game, in contrast to the decision theoretic strategy.
There is something you don't know, which branch of the wave function you're on.
Right, good. Here's what is hard for me to understand about this. This comes out of a tradition of thinking about probabilities epistemically, okay? Of thinking that what probabilities represent are cases of us being ignorant about something. Let me think about what's the right order in which to say stuff here. Let me say it in this order. So there are a couple of things. There are a couple of things that I find puzzling piled on top of each other here. The piling makes them that much more puzzling as a collective. The first thing is, there is this long tradition of thinking, this tradition that goes back to Laplace. If what I know and all I know is that either there's a marble in box A or there's a marble in box B, and I know nothing more, that is my epistemic situation with regard to the question, is the marble in box A or box B, is I have no clue, then there is some kind of a priori principle of rationality to the effect that the probability you ought to assign to the marble being in box A is 50%, and the probability you ought to assign to its being in box B is 50%. This is referred to as a principle of indifference, and the aspect of it I want to focus on is not exactly how you do the calculation, because you guys are going to have different ways of doing it. You're going to have your ESP principle. You're going to have different ways of doing it there. The important feature of it is that it's a priori. Okay, that it enters. It's not
empirical.
That's right. It's not empirical. It enters in as a principle of rationality, and there's something very confusing to me about a strategy like that. That is, when people are asked to offer arguments for a strategy like this, there's a fairly straightforward argument. Well, look, there's a certain symmetry in my epistemic situation. My epistemic situation doesn't distinguish in any way, shape, or form between box A and box B. So when I come to the business of assigning probabilities, in order to be faithful, in order for these probabilities to be faithful representations of my epistemic situation, they must respect these symmetries that are inherent in my epistemic situation. And there's only one assignment of probabilities that respects those symmetries in a case like this. It's the 50-50, okay? And it seems to me that one's reaction to this ought to be, and then, mind you, I mean, you go back in the history, people use this kind of reasoning to show why the probabilities in classical statistical mechanics are what they are. This turns into an explanation of the fact that heat only flows from hotter bodies to cooler bodies and all kinds of stuff like that, okay? All kinds of claims of what's going to happen out there in the world, okay?
I mean, it does work.
Yeah, it succeeds, right, it succeeds. But if this is the reason why if this is offered as the explanation of why heat is flowing from hotter bodies to cooler bodies, it seems to me that you have to say, hold on a second, I must have dozed off there at some point because something happened that seems kind of funny. I went from I have no clue to, of course, I should expect that heat is going to flow from hotter bodies to cooler bodies. I know how to assign precise numerical probability values to various different possibilities. You should say, anybody who hears this should say, did I win the lottery or something? I mean, how did I get all of this for free? Okay, how am I so lucky? And why is it that this constitutes an element of an explanation of physical stuff out there in the world that doesn't give a shit what I know or don't know, acting in some particular way, okay? So you know, that always struck me as profoundly mysterious. And of course, if you examine the argument a little further that I just offered, it's a bad argument. That's not the only thing I can do that respects the symmetries of my epistemic situation. The other thing I can do which respects those symmetries and which seems like a much more honest account and direct account of what my epistemic situation in fact is to say, when I'm asked to assign probabilities to these two possibilities, is to say, which part of I have no clue do you not understand? I have no clue means I have no clue. Of course, I'm not going to assign probabilities to these two possibilities. My epistemic situation is I have no clue. Period. End of story.
If you're forced to assign a probability distribution, you would get that one.
You mean they force me?
No, but I'm admitting.
They hold a gun to my head?
Yeah.
I mean, if somebody held a gun to my head.
You're saying there's another option.
No, it's not. If somebody held a gun to my head, it seems to me the right thing to say to them would be, you're being extremely unfair. Okay, this really isn't nice what you're doing, because there is no rational thing for me to say. Okay, now, as you said, and this is a really interesting difference between this kind of way of justifying probabilities in something like classical statistical mechanics, and this way of justifying probabilities in something like Everett, or in general, what people call self-locating probabilities. In the case of classical statistical mechanics, the things I'm attaching probabilities to are different physical configurations of the world, okay? As you correctly said just now, those numerical assignments of probability turn out to be empirically correct, okay? So all that requires alteration in our attitude towards statistical mechanics, if you were to buy my argument, okay, is if you were to buy my, I have no clue argument, is just that, oh, right, these probabilities weren't a priori. The world isn't doing that because I had no clue. These probabilities turn out to be empirically correct, as you said. And if somebody says, what kind of status do you think they have? It seems to me the correct answer is they have the status of statistical, empirical laws of how the world is arranged, okay? And we believe them precisely because of their empirical success.
Is this a reflection of your Humean upbringing?
I guess, yeah, it is. Good. When we get to, so the summary of the discussion of classical statistical mechanics is you made a mistake here, but the mistake didn't in any way cripple your scientific enterprise. It's just there is this probability distribution. You were right about what its numerical values were. It's just that you thought you could derive it a priori, and that turns out not to be true. Your reasons for believing it are empirical. And if somebody says, but gee, it seems so reasonable to me, the person who has my sort of position will have a ready explanation there. Look, these are true statistical laws, and they're very general ones. There's every reason to expect them to have been very deeply hardwired into us since we were fish, okay, by natural selection, okay? That doesn't in any way put in doubt the claim that they're ultimately empirical generalizations, although they may seem to us extremely intuitive and exactly what we would expect, and so on. Okay.
And you don't think that explanation is available for Everettians?
So here's the difference. In the Everettian case, and let's not talk right away about Everett. Let's just talk about the more general notion of self-locating probabilities. So here's an old example due to David Lewis. Imagine that there are two brains in the world at a certain moment in its history. Imagine that at that moment, these two brains are in exactly the same state, okay? And moreover...
Except they're located in two different places.
They're located in two different places, right? They're in exactly the same state, that is, vis-a-vis their associated mental state, right? They may even have two different bodies or something like that, but their current mental state is exactly the same. Suppose, moreover, that it's part of this mental state that they share that they know there are these two things in the world. Then, Lewis says, each of them could rightly wonder, I wonder if I'm the one on the right or on the left, okay? Even though there's nothing about the physical state of the world that they don't know, okay? And so there could be another kind of uncertainty, unlike the one we were discussing before in the context of statistical mechanics. It's not an uncertainty. It's not anything that you lack knowledge of about the objective physical state of the world, okay? It's something that is compatible. It's a kind of uncertainty that's compatible with complete knowledge of the physical state of the world, just like you have in Everett in the context we've been discussing. But still, there's something you don't know about where you are in there. Okay. And suppose that we were to start a indifference type of argument here. They come up with a priori principles about what kinds of probabilities we should assign. Here, the case is crucially different than in the earlier statistical mechanical case. In the earlier statistical mechanical case, the lucky thing was, you philosophers, you can have all the arguments you like. It doesn't matter, okay, because we have empirical access to what the correct probabilities are. But if two people are having a debate, okay, they're about to split, okay? One of them says, I believe I'm going to end up on the right. The other says, I believe I'm going to end up on the left. A third says, or rather, some single person is entertaining three theories, according to one of which they got a 90% chance of ending up on the right, according to the second of which they got a 90% chance of ending up on the left, and according to the third of which they've got 50-50 chances. In this case, since the probabilities do not attach to claims about the physical configuration of the world, there isn't going to be an empirical access to them. Okay,
we're thinking of these choices as actually arising from a quantum measurement branching the wave function. Yeah. So suppose we with 100% probability, both really do come true somewhere in the wave function.
Both really do come true, but now we're assigning different probabilities to our finding ourselves in one branch or the other. Here, as opposed to the classical statistical mechanical case, what we're assigning probabilities to doesn't have the form of a physical configuration of the world. All the different theories completely agree about the physical configuration of the world. They're just disagreeing about where I'm going to find myself in there. Because they're not disagreeing about the physical configuration of the world, it's obvious that you couldn't set up an experiment, for example, that has the following property. If theory 1 is true, the number 1 ends up being written on a piece of paper at the end. And if theory 2 is true, the number 2 ends up being written on a piece of paper. Because what ends up getting written on a piece of paper is part of the physical configuration of the world. That's going to be the same under any of these circumstances. Okay? So all we're going to have to go on here is the a priori argument. Okay? And if somebody finds the a priori argument unpersuasive, then we really are that really is going to cripple our ability to do physics here in a way that it didn't in the classical statistical mechanical case, because there's not this other non-a priori empirical access to what the right probabilities are. You can say, suppose we run such an experiment repeatedly. Guy splits once, then each one splits again, each one splits again. Okay? Good. There'll be one guy who got all the particles on the left. There'll be another guy who got all the particles on the right. There'll be a much larger collection of people who found some of the particles on the left and some of the particles on the right. Good. Look at the guy who got them all on the left. He says the theory that it's 90% to the left was very well confirmed by what I saw. All the other people, suppose he can talk to them, unlike in Everett. They all start screaming at him. What are you talking about? We confirmed completely different things. Of course, the guy who found them all on the left will say, I knew as a matter of physical determinism that you guys were all going to be there saying this, okay? I'm asking about confirmation or disconfirmation about where I was going to end up, okay? That's confirmed on the left. The guy on the right will say the same thing about the other theory, and all the guys in the middle will say the same thing about the 50-50 theory. Okay? There's not going to be a definitive way to settle this. We might, and I think from a conversation you and I had yesterday, that this might be the reaction you would have in mind. You say, yes, I agree with all that. The kinds of probabilities, how shall I put it? The sense in which one of these probabilistic theories is confirmed or disconfirmed by such experiments is a purely indexical sense, an irreducibly indexical sense. That is, it is not possible, it doesn't make any sense to ask, did this sequence of experiments confirm or disconfirm the theory?
Universally.
That's right. You say that it confirmed it or disconfirmed it for I, you know.
I think the Everettian has to say that because there will be always some real branch of the wave function where everything went screwy for all of history.
No. That's true. But if, for example, if the decision theoretic argument had worked, which I don't think it does, they wouldn't have had to have recourse to this new and metaphysically puzzling kind of purely indexical fact. Okay?
But I think that there will always be people who draw the wrong conclusions in an Everettian multiverse.
Sure. That's right. That's okay if they're, you see, we're going to get into a circularity here, I think. It's fine if there are people who draw the wrong conclusions, as long as it's the case that there's one reason or another not to take them seriously, okay? Now, you might want to say, we don't have to take them seriously because they're implausible.
Yeah,
they're unlikely.
Trying to avoid that.
Okay.
Yeah, that's clearly
but
cheating.
Then we're going to get into
cheating.
Right. And other than that, I mean, if you take on board these purely indexical facts, I mean, it's at this point that that it gets hard for me to see my way clearly through. So we're talking about some new realm of facts, purely indexical facts. And I guess I'm going to want to know a lot about them.
Just in case it's not obvious for the audience, indexical meaning where you are in the universe or some fact of location.
Or let's put it this way. Philosophers call statements indexical, where the meaning of the statement depends on the circumstances under which it's made. Okay, if I say I am wearing a black shirt, that's true. If you say I am wearing a black shirt, that's false. Okay. Yeah. In most ordinary cases, this doesn't cause a problem because we can translate the statements using indexicals into statements using non-indexicals. We could say, no, what's going on here is that David is wearing a black shirt and Sean is not, and we can get rid of that, okay? In the cases we're talking about, the statements we're concerned with are irreducibly indexical. We can't take the I's out of it. We can't take the indexical terms out while still meaning what we want to mean. Okay?
The only difference is which branch of the wave function.
Exactly. So if we really need to take on board into our metaphysics facts like that, in order even to formulate our most basic physical theories, that's a scary and puzzling situation for me. And let me distinguish scary from puzzling. Scary, or maybe scary is too strong a word. Undesirable just because we have other ways of solving the measurement problem on the table that don't require us to speculate about these new kinds of facts. So other things being equal, which of course you will deny that they are, but other things being equal, that should strongly preference the other ones. The second point is it's just puzzling. I need to, so somebody with sort of philosophical inclinations is immediately going to say, whoa, we've got this whole new set of facts here. There's all kinds of things I want to know about how these things work, how they're logically related to one another, what combinations of such facts deductively imply other such facts, and so on and so forth. I want to know a semantics of this kind of talk. I want to know a logic of this kind of talk. You got to give me a few days here, and I got to sit down and think all this through. So first statement. And I don't know, and the sense in which I want to be non-dogmatic here is, I don't know how that thinking would come out. Yeah. Maybe there's a consistent way to talk about all that. Maybe there's not. If there's not, then the view is ruled out in a very decisive way. If there is, then it becomes more of a balance between various desiderata that we might have.
Scary but exciting and exhilarating at the same time.
Cup half full, cup half empty. In my tradition, you maximize regret.
All right. We've reached our little cutoff here, so I have not maximized regret. This was great. Thanks, David, for being on the podcast.
Thank you for having me. It was lots of fun.